In this section, we want to start taking a look at how we can solve a system of two equations with two variables. But before we start getting into that problem-solving process, we want to talk about what our solutions look like and how we know we have a valid solution to that system. So a linear 2x2 system consists of two equations and two variables. All solutions will be of the form open parenthesis x, comma y, close parentheses, meaning our solutions will be a coordinate pair. If a particular coordinate pair, x comma y, is a solution to that linear 2x2 system, then it will make both equations true. So when we're solving these systems, our final result will be a coordinate pair, some x and y value. And for that coordinate pair to be the solution, we have to know that it makes the first equation true and it makes the second equation true. In example 1, we're given two potential ordered pair solutions to the system of equations, which we'll reference as equation 1 and equation 2. What we want to do is verify which of these 2 points is a solution to the system of equations. We'll start with the coordinate pair in part A, 8 comma negative 27. And what we'll do is plug those x and y values into equation 1. So wherever y occurs, we'll plug in a value of negative 27. And wherever an x occurs, we'll plug in a value of positive 8. And then we'll evaluate both sides to see if this makes a true statement or a false statement. On the left-hand side, there's nothing to simplify. This is just negative 27. On the right-hand side, we'll have negative 2 times 8, or negative 16, minus 11, which will give us negative 27 is equal to negative 27. So that ends up being a true statement. When we made those substitutions for x and y, the left-hand side of the equation equals the right-hand side of the equation. But knowing that it's a solution to one of those equations isn't enough. We need to make sure that coordinate pair makes both equations true. So now what we'll do is plug in y equals negative 27 into the second equation. And then we'll simplify and check whether the two sides of this equation are equal. On the left-hand side, we get negative 27 will be equal to 5 halves times 8. That will become 20 because we'll be able to reduce 8 over 2. So this will become 5 times 4, or 20, minus 2. And we get negative 27 is equal to 18. That's clearly an incorrect statement. So, since this coordinate pair did not make both equations true, this is not a solution. Or to be more clear, 8 comma negative 27 is not a solution to this system of equations. Next, we'll check the coordinate pair we have in part B, negative 2 comma negative 7. We'll start off with equation 1 again, plugging in negative 7 for y, and negative 2 for x, which will give us negative 7 is equal to negative 2 times negative 2 minus 11. This will give us negative 7 is equal to positive 4 minus 11, or negative 7 is equal to negative 7. That's a true statement. Both sides of the equation are equal when we make those substitutions. Now we need to check the second equation and see if we still end up with a true statement. Now we'll plug y equals negative 7 into the second equation, giving us negative 7 is equal to 5 halves times, in place of x, we'll plug in negative 2. minus 2. Now to evaluate this, when we multiply 5 halves times negative 2, the 2's will cancel, leaving us with a negative 1. So we'll have negative 7 is equal to negative 5 minus 2, or negative 7 is equal to negative 7. When we plug that xy coordinate pair, negative 2 comma negative 7, into both equations, it makes both equations true. So that is a solution to the system of equations. And again, in part A, as soon as that coordinate pair fails to make either of the original equations true, we know we don't have a solution to that system.